local maximum value and local minimum value of a function in two variables. Let's at first remember how to find local extreme values for a function in one variable. If we have a function y equal fx and a in the domain of the function, and let's suppose that the function is differentiable at the point a. So this means the derivative exists. So let's suppose that the derivative of f at the point a is 0. This means that the point a is critical point for the function fx. And let's suppose we have two cases here. Maybe f derivative, second derivative greater or equal 0. When f derivative, second derivative at a bigger than 0, or the second derivative at a smaller than 0. So in this case, the first case here, the concavity will be up. So the point AFA here is local minimum. But if the second derivative is smaller than 0, so the concavity is down and FA is local maximum. Let's suppose here that it's bigger, strictly bigger than 0, and here strictly smaller than 0. So we will do something similar to find extreme values for function in two variables. So before that, let's take what is a saddle point. What is a saddle point of a function in one variable? If the point A is critical point for the function f, this means the derivative at this point is 0, but the point fa is not local minimum and not local maximum. So in this case, the point A is called saddle point. For example, let's take this function y equal x power 3. So at the point 0, the derivative, the first derivative of y derivative equal 3x power 2. So if I put x0, so the derivative is 0. So f derivative at 0, this is fx. So derivative at 0 equals 0. But using the graph of the function, f0, which is 0, is not local maximum and not local minimum. So the point 0 is saddle point for the function x power 3. So we will define the saddle point now for a function in two variables like this. If the gradient of the function f at a point AB equal to the vector 0, and this means that partial derivative of f with respect to x at AB equals 0, and a partial derivative of f with respect to y at AB also equals 0, but FAB is not an extreme value, so it's not local minimum and not local maximum, then AB is called, the point AB is called saddle point of the function. So the surface of the function will be something similar to this one. So it will be something similar to this one. So here, any point here, it's a saddle point. So the tangent plane at this point is horizontal, but this point is not local. F of the function at this point is not local max, not local minimum. Theorem: if the function z equal fxy differentiable at a point AB, and if the value FAB is local extreme value, this means local maximum or local minimum, then the gradient of the function will be 0. Because if it's local extreme value, so if it's local minimum like this, so the tangent plane here will be horizontal, so the gradient will be 0. And if it's local maximum, it's also the same. So let's take an exercise. Let fxy equal e power x3 plus y3 plus x. Evaluate all local extreme values of f on his domain. What is the domain of the function f? The domain of the function f is all of the plane r power 2. So let's calculate the gradient. What is the gradient of the function f? It's partial derivative of f with respect to x. It's 3x power 2 plus 1 times e power x3 plus y3 plus x times I plus 3y2 times e power x3 plus y3 plus x times j. Remark that this term is different from 0, and also this one is different from 0. So this term here will not be, it's not equal to 0. So because this vector is not 0, so my vector here is not vector 0. So the gradient of f at xy is different from vector 0 for each xy, whatever the point xy in the plane r power 2. So f doesn't have any extreme local extreme value, any local extreme value. The next exercise or theorem, let's take theorem. Let's suppose that we have a function z equal fxy, and let's suppose that this function is differentiable at the point AB, so AB in the domain, and the gradient of the function at AB is given by partial fxi plus fyg. And let's suppose that this is equal 0. When I suppose this is 0, so I suppose that the point AB is critical point for the function f. Let's use this notation now. Delta xy, it's a function in xy, equal determinant of f, partial derivative of f with respect to x2 times partial derivative of f with respect to xy, x to x, then to y. Partial derivative of f with respect to y, then to x, and fyy. Remember that fxy by theorem equal fyx. F, the derivatives of second order are continuous. So this determinant equal to fxx times fyy minus fxy power 2. Now, the theorem said that if the determinant, if delta here is positive, and if the second derivative is positive, then f at AB is local what? Minimum. Remember, for the one variable, when we said here, so this is the second derivative of f with respect to x at A. If the second derivative is positive and the first derivative 0, so I have local minimum for function in one variable. So here we have something similar. So here it was first derivative 0 and the second derivative positive give me local minimum. Because second derivative positive will give me something like this, so I have local minimum. So here I have something similar. So here the second derivative with respect to x positive, and the gradient equals 0, so it's similar. This condition, first condition, is similar to the first derivative equals 0. And I have another condition here, extra condition. So if this is satisfied, so FAB is local minimum value of the function z equal fxy. Now, if the delta at AB positive and fxx at AB is negative, so here FAB is local maximum, because the graph of the function here, value of the function, because the graph here would be something like that, and I have at the point here AB, I have concavity down, but here I have the first derivative. When the first derivative, second derivative positive, it will be something like this. So local minimum. Okay. Now, case number 2. If delta less than 0, then the point AB is a saddle point for the function. What is the meaning of saddle point? So remember, it will be something like this. Any point here, the tangent plane at this point is horizontal, but this point is not. This is point A. This point here is A, B, F, A. So this point here, M, the tangent plane at M is horizontal, but M is not, FAB is not local maximum value and not local minimum value. If delta equals 0, so no info. This means sometimes delta equals 0 and the point AB, FAB will be local maximum. Sometimes delta equals 0 and FAB is local minimum. Sometimes delta equals 0 and FAB, it's not extreme value for the function. Let's take the first exercise. Z equal x power 2 minus y power 2. So I have this function fxy equal x power 2 minus y power 2. Find each local extreme values. Let's calculate the gradient of f. Its partial derivative with respect to x, it's 2x I minus 2y j. If we put this equal 0 to find the critical points, so we'll have x equal y equal 0. So we have this point 0, 0 is critical point. Critical. So now let's calculate the delta at this point, at xy. So delta is given by determinant so I have fx, it's 2x, and fy minus 2y. So let's calculate fxx, it's 2, so let's write here 2. What is fyy? It's minus 2, so let's write minus 2 here. Let's calculate fxy, so it's 0, and also fyx is 0, so here 0, 0. So delta equal minus 4 for each xy. So delta at 0, 0, the answer is minus 4 negative. So the point 0, 0 is a saddle point of the function z equal x power 2 minus y power 2. Let's see the picture or the graph of the surface of the function x power 2 minus y power 2. So here, this is the surface of here you can see the surface of so this is the surface of z equal x power 2 minus y power 2. Okay, and you can remark that the point here, the red point here, it's the point 0, x0, y0, and also z0. So at this point here, the tangent plane is horizontal, but this point, but f0, 0, what is the answer of f? Because this is fxy. This is fxy. So f00 equals 0. So this value 0, it's not local maximum and not local minimum of this function. Let's go back to our exercise. So let's take another exercise. Next exercise. Exercise, find all local extreme values of the function z equal x power 2 plus y power 2. So here let's calculate what is the partial derivative of f with respect to x. It's 2x. Partial derivative of f with respect to y equal 2y. To find the critical points, let's put fx equal fy equal 0. So you will have x, y equal 0, 0. This is critical point, as critical. This is critical point. Now let's calculate delta at xy. So this is determinant of here, the second derivative of the, f with respect to x. Derivative of 2x here is 2. Derivative of 2y also 2. Fxy 0, fyx 0. So the final answer is 4. So what is delta at 0, 0? The answer is 4, bigger than 0. So let's calculate now. We are using the theorem now. This theorem. I have delta bigger than 0. So let's calculate fxx at 0, 0. If it's bigger than 0, so it's local minimum. So fxx at 0, 0, the answer is 2, bigger than 0. So the point, so f 0, 0, which is equal to 0 power 2 plus 0 power 2, which is 0, is local minimum value of the function f xy equal x power 2 plus y power 2. Let's see the picture of the graph or the surface of the function. So this is here. So here you can see the surface of this function. The function z equal x power 2 plus y power 2. So the point here, you can see a point here. This point x0, y0. So here the x-axis. So you can see here x0 and y also 0. Okay, and z also will be 0. So, and this is also local minimum value of the function. So this is fxy. So we can remark that f0, 0, which is 0. This is local minimum value. Okay, let's go back to our exercise. Let's take this exercise, find all local extreme values of this function. Let's calculate fx. What is fx? It's 3 x power 2 minus 1. Let's calculate fy. It's 3 y power 2 minus 4. To find the critical points, let's put fx equal fy equal 0. So you will have x power 2 equal 1 and y power 2 equal 4. So x equal plus minus 1 and y equal plus minus 2. So we have, let's write in another color, all critical points are these points. The first point, x1, y2, second point, x1, y minus 2, third point, x minus 1, y2, the last point, x minus 1, y minus 2. Now let's calculate delta, the determinant at xy, which is determinant of fxx here, 6x, here fxy, it's 6y also. Here fyy, here fxx. Now fxy here it's 0, fyx here 0. So the final answer will be 36xy. So let's calculate delta at the points -1, 2, and delta at the point 1, -2. So delta will be negative at these 2 points. So these 2 points, -1, 2, and 1, -2 are saddle points. Now let's calculate delta at the point 1, 2. And we will find that this is positive, and delta at -1, -2 also positive. So what is fxx at 1, 2? So the answer will be 6 times x. So 6 times 1, so it's 6. So it's positive. So f12. What is the answer of f12? Let's calculate. We have here, let's write in another color, in red, for example. Here 1, here 8, -3, -24, plus 1. Okay. So we have here -16, 8 -24 -16, 2 -3 -1, so -17. So this is -17 as local minimum, Now let's continue. Let's calculate. Now what is fxx at the point -1, -2? So the answer is -6, negative. So f -1, -2 will be local maximum. Let's calculate f -1, -2. Let's delete this here. Let's repeat in green, for example. So here it's -1, x -1, y -2. So -8, and here +3, y -2, so +24, +1. So 24 -8, so it's 16. -1 with 1 deleted, 16 +3, so it's 19. So the answer here is 19 as local maximum value of the function f. So we have 2 saddle points and 1 local maximum, 1 local minimum.